So, good evening, everyone. Let us continue our discussion into the 10th week lectures. So, let us start revising the contents. So, in this week, we would be basically focusing on the design of the staircases. Okay. So, that is a relatively small design as compared to beam, column, and slab, but it is an important one, mainly for a multi-story building. So yeah, so let us start. So these are the examples of staircases, as you all know, and this is an example of a dog-legged staircase. So here, if you see, the shape of the staircase is like that of a leg of a dog, right? So yeah, so basically, in staircase or the designing of staircase, or if we say like if we focus on stairs, basically, so there are a set of steps, right, which are arranged in a inclined, a vertical inclined order. Okay, so each step basically it has two parts. Okay, one is the rise, that is the vertical portion, and the second is the tread, which is the horizontal portion. Okay, and this tread again, it can be divided into two further two parts, that is the nose and the going, nosing and the going. Okay, so this nosing is basically the distance from the end, from the perpendicular distance from the end of the your this the lower point of the rise. Okay, so the extension basically, that is the nosing, and the remaining other part is the going. Okay, so basically going you will see everywhere, but nosing will only be possible if it is an inclined step. Okay, so nosing will not be available in this case. Okay, that is a complete simple stair, okay, which is perpendicular to the say horizontal. When the rising is perpendicular to the horizontal, there is no nosing. Okay, only when the rising is at an inclined angle, uh, to the vertical. Okay, so then only we will get this extension, which is basically the nosing. Okay, and basically this lower part of the steps, that is called the waist. Okay, so yeah, so basically these are 4 5 terms which we require. Basically the mainly the rising and the trade. Okay, so rise and the trade, so that those are the most important terms. Okay, and others are also significant. Okay, so yeah, so there are some recommendations as per IS code. Okay, so what should be the dimension of trade and rise? Okay, what should be the value? Okay, so there are some standard values. Okay, so for the case of houses, okay, and factories, so basically the thread is kept as 250 millimeter. The ideal length of the thread should be 250 millimeter. That is the horizontal distance should be 250 millimeter. Okay, and in the case of public buildings, it can be increased from 270 to 300 millimeter. Okay, so basically, it should be 25 centimeter in case of houses and factories, and it should be increased to 27 to 30 centimeter in case of public buildings. Okay, so that is the trading or the horizontal distance. Okay, and in the case of rising, the values are values should be smaller than the trade. Okay, so here it is 25 in the case of houses and factories. In case of the houses and factories, it should be for rise it should be 16 in the case of residential building, and 16 centimeter or 160 mm. In case of factories, it should be 190 millimeter. Okay, so it should be less than 250. Okay, and in the case of public buildings, it should be 150, further less. Okay, because a lot of people, there will be influx and outflux of lot of people. Okay, so that's why it should be as smooth, as efficient as possible. So lower is the rise, better it is for movement. Okay, so it should be 150 millimeter in the case of public buildings, and 190 for factories, and 160 mm for residential buildings respectively. And after taking these values, it should also obey these equations. Okay, so it should be, so this equation basically, so it should be that the twice the value obtained by multiplying the rise with 2 times and adding with going. Okay, so 2 times the rise plus going it should always be in between 550 and 700 millimeter. Then only it will be an ideal value, acceptable value. Okay, so these are some of the parameters and some of the conditions as per the IS codes, which we need to focus or keep in mind while designing. Okay, so basically, here the while for the design of the staircase, basically we basically consider the effective span. Okay, so that is how to calculate that. That has been defined in clause 33 or 33.1 of in page 63 of IS 456. Okay, so effective span is basically the summation of s plus x plus y. Okay, where s is basically the span of the staircase. Okay, and x and y are the extension. Okay, extension of the in the landing area. So this is basically called the landing area. Okay, and this is basically called the flight. Okay, so it is flight because it is going up, right, like an aeroplane. We are going up. Okay, so that's why it is called flight, and these positions are called the landing area. Okay, so generally, if this landing area is greater than 1 meter, okay, so the value of x should be half of that. Okay, if it is less than 1 meter, and if it is greater than 1 meter, and if it is less than 1 meter, then we take the value of x as 1, simply 1. Okay, so uh, it should be minimum of 1 and the total distance divided by 2. Okay, so that is the condition. Okay, so yeah, so that is the conditions required. First we got understood the condition, then parameter required for rising and going, the values, and secondly the effective span and the span of the staircase, and the xy value we understood what it is all about. Okay, now let us go to load. Okay, so what are the loading values, okay, as accepted by the IS code. Okay, so the load value for staircase as per IS code for residential building, okay, it should be 2 kilonewton per meter square. Okay, so that is because in residential building there is no overcrowding. Okay, so that's why this is 2 kilonewton per meter square, and therefore the condition is it should not be liable to any overcrowding. And as like as can be expected in residential building, there will not be any overcrowding. Okay, because there will be only a family living. Okay, however, in the case of public buildings, okay, public means it will have lot of people. Okay, lot of influx and outflux, so lot of movement, so there will be definitely be overcrowding. That's why the load for design is more than twice. Okay, so it is 2.5 times, so we take 5 kilonewton per meter square. So for residential building, the load taken should be 2 kilonewton. Okay, like if if we have to, that is basically the design load. If we don't know what to take, we take 2 kilonewton, okay, per meter square. And for public buildings, we can take 5 kilonewton per meter square. So it is because it is liable to overcrowding. Okay, so that is, these values are given if these values are can be taken if we don't know. Okay, we don't know what is the load. But if we have to calculate the loads, okay, so what is the calculation of dead load, and if we know what it should be, it is okay, so then we can use this formula. Okay, so how to calculate the dead load basically? So for dead load, we basically have three loads. Okay, one is the load of dead load of waste slab, that is this portion. Okay, second is the dead load of waste dead load of each step without waste slab, that is basically this portion. So this is basically a step. Okay, this is basically a step. So this is the tread. Okay, this is the rise. Okay, this is the going part, this is the nosing part. Okay, and this is the uh, it is basically the width. Okay, width with the along the waist. Okay, width along the waist. Okay, so this value will be nothing but, according Pythagoras, it is square root of r square plus g square. So that is what it is written here. Okay, so this is used for finding the dead load of each step without waste slab, without this portion, only this portion, it is this load. Okay, this rectangle portion, sorry, this rectangle portion, it is basically this load. And there is one more load. Okay, if it is given. Okay, so that is the dead load for floor finish. Okay, so that may or may not be taken into account while calculation. Okay, but these two loads are must. Okay, and this 25 is nothing but the unit weight of concrete. Okay, and to get it per meter width, okay, we divide the value by g. Okay, which is the going value. Okay, so that is how it is calculated. Okay, and that is the ideal that is the way how to calculate the dead loads. Okay, so And because also we can say, because this is the design considered load, if we don't have the dead load, so we can also say that this load should be ideally be less than these two values. Okay, for residential building it should be less than equal to 2, and for public building it should be less than equal to 5, because these are the ideal loads. So if we don't know, we consider that, that means from calculation it should be ideally be less than or equal to that load. Okay, so let us understand this by going through a solved example. Okay, so the problem is a longitudinal type of staircase. Okay, the longitudinal basically means a staircase. Okay, so it is a staircase which is straight. Okay, firstly it is straight, and secondly the flight the this one the flight is basically, the flights are basically, or the stair is basically connected at the ends. Okay, not at the transverse portion. Okay, and that too through landings. Okay, so if that happens, then it is called the longitudinal staircase, because the staircase, the stairs are connected at the end by the landings. Okay, there is one more staircase which is called the transverse staircase. Okay, so in that case there will not be any landing. Okay, so it will be just be connected through the wall. Okay, in the transverse portion. Okay, in the not at the ends, at the transverse portion, basically in the body it will be connected, so it will be like a cantilever. Okay, so it will be like a cantilever, so that is called a transverse staircase. Okay, so this is basically a longitudinal, whatever we have studied now, say for example this. Okay, this is a longitudinal staircase because this is connected at the ends. Okay, through the landing area, right? In transverse staircase there will be no landing, there will be only a wall. Okay, the staircase will be connected through the wall. Okay, so that will be basically the stair will be cantilever, we can say, right? So yeah, so the a longitudinal type of staircase spans a distance of 4 meters center to center of beams. Okay, so at the landing there is beam. Okay, so it is a staircase spanning a distance of 4 meters center to center of beams. The values of rise, going, tread is given. Okay, R is 160, G is 250, and T is 270 millimeters. Right. The treads have 115 millimeter granulatic finish. Okay, and granulatic is basically similar to this mortar. Okay, cement, sand, and water mortar, something like that. So it is having a finish of 15 granulatic. Okay, the trades, and consists 16 steps. Okay, so number of steps are 16, and we have to consider concrete of grade M20 and steel of grade Fe 415, right? So design the staircase for a live load of 5 kilonewton per meter square. Okay, and breadth of the staircase is 1.5 meter. Okay, so yeah, so the live load, okay, that has been given as 5 kilonewton per meter square. Okay, and the breadth of the staircase is 1.5 meters. Okay, and let us assume 12 millimeter diameter of rebars and 15 millimeter clear cover. Okay, so that is, we have to design a staircase based on the given conditions. Okay, so the first step will be the calculating the thickness of waste. Okay, what will be the W value? Okay, so for this, we have to initially find the effective depth, this D value. Okay, so and we have to find this, and at the last step, we have to even check that the L by D value is the slenderness ratio basically. So it is within the acceptable limits. Okay, because we are assuming this, right? So let us assume the L by D value as 30. Okay, so we have to check it also, like at last whether it is under acceptable limits. Okay, so considering this L by D value is 30, we get the D value to be 4000 by 30. So the span is basically 4 meter, right? And it is 30, so effective depth, capital small d, will be spanned by 30, right? So 4000 by 30, which is 133.33 millimeters. So that is small d, effective depth. Okay, so if we add this effective depth with the clear cover and half of the rebar diameter, right? So we will get the total W value. In case of beams, we call that total actual depth, capital D. In case of staircase, it will be waste, W. Okay. So that W will be 133.33 plus 15 plus 12 by 2, which comes out to be 154.33 millimeter, right? So this is the minimum required amount of waste, okay, which is required for a span by effective depth value of 30, that is slenderness ratio, and a clear cover of 15, and rebar diameter of 12 mm, right? So that is the minimum required. So let us take it to be 160 millimeter. Okay, let us take the thickness of waist to be 160 millimeter. So taking 160 mm, the effective depth therefore will be 160 minus 15 minus 12 by 2, which is 139 millimeter. So our for our staircase, the effective depth will be 139 millimeter. Okay, so that was the first step. Okay, the second step is basically the calculation of dead load for the staircase slab, from staircase slab. Okay, so that is the dead load. Okay, from each step of this, because dead load we calculate for each step. Okay, and that's why it is in kilonewton per meter square per unit width and per unit meter. Okay, so the number of steps we just have to multiply by the length. Okay, so one step we need to just find out the dead load. Okay, so as we just discussed, okay, so there are basically three terms. Okay, one is uh, the dead load for the step without the slab. Okay, so which is basically your this WB into 25 by G, this the dead load for this portion. Okay, that is WB into 25 by G. Okay, second is the dead load for the waist. Okay, waist of the this one waist lap. Okay, basically, so the dead load due to waist lap, that is calculated using this formula. Okay, which is R sorry the dead load of waist lap is basically calculated by this WB into 25 by G. Okay, that is basically for this. Okay, I'm sorry, and the dead load for this basically that is calculated using this. Okay, so that is half into RT into 25 by G. Okay, so that is for this. Okay, and this is the third. Okay, which I told you a few slides back also. So if we have to calculate a dead load for floor finish, okay, which was not given there, so here they have asked to consider, because there is 15 millimeter granulated finish. Okay, so we have to consider this. So here the dead load will be for floor finish, it is calculated using FT, using the value formula FT by G into 23.5, or FT into 23.5 by G. Okay, so here the 25 is basically the unit weight of concrete, right? In this case, the this one, the value of 23.5 is basically the unit weight of floor finish. Okay, so unit of weight of concrete is 25 kilonewton per meter cube, and unit weight of floor finish is considered as 23.5 kilonewton per meter cube. Okay, and this B, as I told you, it is the length of each step. Okay, across the waist lap. Okay, so that is using Pythagoras, it is square root of G square plus R square, right? So the value of going is given as 250 millimeter, and the value of rising is 160 millimeter. So putting the values, we get the length of each step across waist levels, or the value of BS 296.81 millimeter. So rounding, we get 297 millimeter. Okay, and the other values are known. Okay, so the W value is yeah, your W value is 160, right? 160 millimeter, this waist. Okay, B value is 297, we just calculated. Okay, R value is 160. Okay, so your T value is 270. Okay, and yeah, so these are the basically the values. Okay, and your F value is 150 millimeter. Okay, and your T value, yeah, it is 270, right? So these are the values. Okay, so substituting the values, we get the dead load as 7.2927 kilonewton per meter square. Okay, so that is the value of dead load. Okay, and the live load was given as 5 kilonewton per meter square, right? So adding dead load plus live load, okay, so adding both the loads, we get the characteristic load as 7 plus 5 is 12, so 12.2927 kilonewton per meter square, that is the characteristic load. Okay, and from there we can get the design load or factored load just by multiplying with 1.5. So multiplying 1.5, we get the limit load, design load or character factored load as 18.439, okay, kilonewton per meter square. So that is the design load. Okay, so this is the load. Okay, so yeah, so based on this load, we now have to calculate. Okay, so the bending moment basically this is an empirical formula. So the bending moment per meter width of staircase is always taken as WL square by 10. Okay, so that is a formula basically empirically found. So taken considered as per the IS code. So W is 18.44. Okay, L is 4 meter. So substituting, we get the mu value as to 29.504 kilonewton meter. Okay, so using this limiting moment condition, which we have studied from the first class itself, first second class itself. So this limiting condition moment value is nothing but 0.138 fck bd square equal to mu, right? For Fe415 grade of steel, right? For Fe500 it is 0.133, and for Fe250 it is 0.149, right? So here we need to find the effective depth value, and that value should be, okay, lesser than what we have taken. Okay, it should not be more, otherwise our considered d value is not satisfactory. Okay, so that will the section will not be safe. Okay, so here FCK value is 20. Okay, B value is 1000 because it is per meter width of staircase, and D we have to calculate, and MU value is 29.504, okay, into 10 to the power 6 Newton millimeter, right? So substituting the values, we get the effective depth value is 103.39 millimeter. So that is the required effective depth. Okay. So the required effective depth is 103.39 millimeter, and we have got the effective. We have taken the effective depth as 139 millimeter. So as required effective depth of 103.39 millimeter is less than the considered effective depth of 139 millimeter, so the structure is safe. The structure staircase is safe. So our D condition is satisfied for the required loading. Okay, now we have to calculate the area of steel. Okay, area of the reinforcements required. So we know that mu value can be also written as point from the area of concrete. It can be written as 0.36 fck x by d into 1 minus 0.416 x by d into bd square, right? So if we just divide by the whole equation, if we divide by 0.36 into 0.416 x by d into fck bd square, if we do that, we get it to be 6 point. We get the equation transforms into 6.68 mu by fck bd square, which is equal to 2.40 into x by d minus x by d whole square. Okay, and even taking the leaving x by d on one side and shifting the other terms the other side, we get x by d equal to 1.2 minus 1.2 square minus 6.68 mu by fck bd square whole to the power half. So I think we have already discussed how we have derived this, okay, in singlet doubly reinforcements, reinforced beams. Okay, so this is the equation basically. So substituting the values of mu and fck and b and d. Okay, so D is 139, B is 1000, FCK is 20, MU is your 29.504 into 10 to the power 6. So substituting the values, we get the x by d value as 0.2356, right? So that is the x by d value. And from this we can get the lever arm, okay, which is basically Z equal to D into 1 minus 0.416 or 42 into x by d, okay. So D is 139, x by d is 0.2356. So substituting the values, we get the depth, the lever arm depth as 125.36 millimeter, right? So using this value and using this formula to calculate the moment from the tension side, which is limiting moment basically, so which is 0.87 fyz into ast into mu, into ast equal to mu, right? So substituting, we get substituting the values and your calculating the area of steel, we get your mu value is 29.5, fy is 415, z is 125.36. So area of steel will be just we have to substitute, and we get it to be 651.86 millimeter square per meter width. Okay, so that is the area of steel required. Okay, and this is per meter width, and we have the given yeah meter, the width to asked to be taken is 1.5 meter, right? So therefore we are multiplying it with 1.5 meter. Okay, so therefore the total steel required will be 651.86 into 1.5, which is basically 977.79 millimeter square. Okay, so that is the area of steel, okay, that will be required for each step. Okay, so the number of bars, okay, so the number of bars that will be required is basically this much, or uh, yeah. So the number of bars, basically, taking the rebar diameter is 12 millimeter dia. So the number of bars will be 977.79 by 113, which is the area of one bar. So that comes to be 8.6, comes out to be 8.65. Okay. So that means we need 9 numbers of 12 dia bars. Okay. So therefore the percentage of steel will be how much? It will be 9 into 113 divided by 1500, which is the area, width, okay, width of the staircase, into 139, which is the effective depth, or the depth of the effective depth of the waist, right? So into 100. Okay, so that comes out to be 0.48%. Okay, so that is the that is the given, okay, provided value. And yeah, so that is the primary reinforcement. Okay, and we can also further provide the distribution steel, which is a secondary reinforcement. Okay, so as per is code, okay, it should always be uh, it should be like, for HYSD bars it should be a minimum of, or it should be provided of 1.12%, right? So 0.12% is for HYSD, and 0.15% is for your mild steel, right? So that is the amount of steel that needs to be provided, okay, minimum. So therefore the distribution steel will be how much if we take per meter width, okay, and d value is taken as 160 instead of 139. Okay, so the area of steel is, for the distribution, it will be 192 millimeter square. Okay, so if we consider 8 dia, okay, so for considering 8 dia, we get a spacing of 26.18, 26 261.8 millimeter. Okay, so that is the required spacing. So if we take lesser, it is even better. So let us take 250 millimeter. Okay, so if we take 250 millimeter and provide 8 bars, okay, so we get area of steel about 200 millimeter square, which is more than 192. So if we would have taken 261.8, we would have got 192. But because we have taken 250, it will be more. It will be 200 millimeter square. Okay, so that is almost we have designed. So we will now check for the check for the various cases like shear and deflection and all. And yeah, so all these cases. So for the shear, the V value we calculate, that is WL by 2. Okay, so W is the load, 18.44 into length 4 meter divided by 2, which comes to be 36.88 kilonewton per meter width. Okay, so from this we can calculate the gamma V value, right? So that is nothing but 36.88 kilonewton divided by per, because it is per meter width. So this is 1000, 1 meter, okay, into, that is B into D, right? So B is 1000 and D is 139, small the effective depth. So that comes to be 0.26 Newton per millimeter square, okay, and that is lesser than the minimum shear strength of concrete. Okay, so minimum design shear strength of concrete for M20. Okay, so if you see table 19, the minimum value is 0.28. Okay, so it is even lesser than that. Okay, so that means we don't actually require any sort of your shear reinforcements. Okay, no requirement of any stirrups or tie bars. Okay, or inclined stirrups. Okay, so therefore it is safe in that aspect. Okay, from shear. Okay, but we can give if we require, if we want to, but we don't require any. Okay, because it is less than the design shear strength of concrete. So therefore it is safe. Now we also check for the deflection. Okay, so deflection, as I think I told you in the question start itself, that we have to, although we were assuming the value to be 30, but we have to check it. Is it okay? Is the value of L by D as per the allowable limits? So the percentage of steel which we took is 0.48. Okay, and the L by D value, this is the maximum allowable limit for continuous beams. Okay, so we are taking here continuous because the staircase is extended to the first floor. Okay, throughout it is extended, so we take it continuous. We consider it to be a continuous member. Okay, so it can go beyond first floor also, so it is a continuous member. So here, as per clause 23.2.1a, page 37 of IS 456, the L by D value is 26. Okay, so our value has to be lesser than the allowable limit. Okay, so this is the basic value. For tension reinforcement we have to apply some modification factor also, so that is calculated as per the figure 4. Okay, present in page 38. So from there we will get that. Yeah, so I think it was the formula was zero point 0.5 Fs formula was 0.58 Fy into area of steel required by provided. Okay, something like that. So required was 977, provided is 9 into 113. Okay, and into 0.58 into 415 gives 231.23 Newton per millimeter square. Okay, so that is the value of Fs. Okay, and percentage of steel is 0.48. So using these two, we get the value of F2, which comes out to be 1.3. So therefore allowable L by D will be 1.3 times 26, which is 33.8. Okay, and the L by D value which we got for our case, it is 4000 by 139, which is 28.78. Okay, and this value is less than 33.8, right? So it is safe. Okay, so because it is less than, because L by D slenderness ratio limit is achieved. Okay, so it is within the acceptable limits, and because design shear strength is also of concrete is more than the shear. Okay, shear stress. Okay, and also because the effective depth, okay, which was calculated was which was considered was higher than the required effective depth. So because all the three cases are satisfied, we can say that our staircase is the section is okay. Okay, it is satisfied. So that is how we have to design the staircases. Okay, so with this we today the 10th week lecture is the lecture discussion is finished. Now let us go to the solve problems. Okay, let us understand further by solving the problems. So this is relatively a small class, I feel, but it is an important one because staircase is required everywhere, right? So okay, so let us start solving problems. The first question is, a dog-legged staircase is consisted of steps with tread and riser depth as 180 millimeter and 130 millimeter respectively. Okay, so addition to that, uh, it has a landing slab one side of its flights, and its width is 1200 millimeter. If the floor to floor height of a building is 2860 millimeter, then total number of tread T and riser R in the staircase will be how much? R equal to 20, T equal to 18, R equal to 18, T equal to 16, R equal to 16, T equal to 14, or R equal to 22, T equal to 20. Okay. So basically it is a dog-legged staircase. That means there will be in one story, there will be two flights. Okay. And in between there will be a landing area. Okay. So that is a dog-legged because the shape is like a dog leg. Okay. So it has it has a tread for each step. The tread length is 180 mm and riser depth is 130 mm. Okay, and the landing yeah, so because dog legged it has a landing slab. Okay, and in between, and the width is how much? 1200 millimeter. Okay, so width of the steps. So if the floor of and the floor to floor height is, that is the story height is 2860 millimeters, so we need to find the tread and rise, right, of the staircase. So yeah, so this is the dog legged staircase. Okay, so here the floor to floor height is 2860 millimeter. Okay, and the depth of riser is how much? It is 130 millimeter, right? So dividing the number of the floor height with the depth of one riser, we get the total number of risers. Okay, which is 22. Okay, so dividing 2860 by 130, we get 22. Okay, and the relation between riser and tread. Okay, so the relation between riser and tread is that for one flight. Okay, for one flight, the number of tread is the number of riser minus 1. Okay, so for one flight the number of treads present will be the number of riser present minus 1. Okay, in this case there are two flights. Okay, so this is one flight, this is one flight, as you can see, because it is a dog legged staircase. Okay, so therefore there are two flights. Okay, so therefore the number of treads, the total number of riser is 22. Okay, but because there are two flights. Okay, so for each flight there will be one less tread. Okay, So that is the this one. The trade number for one flight, the number of trade is 1 minus number of riser. For two flights, therefore, the number of trades will be 2 times 2 minus the number of risers minus 2. Okay, we have to subtract for each flight 1 1. Okay, so therefore the number of trades will be 22 minus 2. Okay, which basically is 20. Okay, because there are two flights. So therefore the number of riser is 22 and number of trades is 20. So as per this, the correct option is D. Okay, so as you can see, D is the correct option. Second question, match the set A with set B. So set there is A stringer beam, B handrail, C finial, D nose, and set B is one step to bottom of steps, three newel, four baluster. Okay. So what is the correct combination? First choice is A1, B2, C4, D3. Second choice is A2, B4, C3, D1. Third choice is A2, B1, C4, D3. And fourth choice is A4, B2, C3, D1. So what will be the correct choice? Okay. So initially, let us understand what are these terms. Okay. So first is the stringer beam, right? So stringer beam is basically the beam, okay, that is present in the in this waist area. Okay. So in the waist area, if any type of beam is present, that is called the stringer beam. Okay. So if you see here, so yeah, so stringer beam will be connected to bottom of steps because it is always present below the step. Okay, so it will be bottom of the step. So stringer beam will be bottom of steps. Okay, so as per this, A is 2, that is either B or C will be correct. Okay, second is handrail. Okay, so handrail is, yeah, so this is the handrail. Okay, as you know, this is the handrail. Okay, and if you see all this, okay, so the step is this. Okay, bottom of steps is the bottom of the step portion. The newel is this. Okay, and the baluster is what? Yeah, so baluster is this. Okay, so we can say that the handrail, okay, it is connected to the baluster, or the handrail is present over the baluster. So baluster is basically this vertical strings. Okay, so handrail is present over the baluster, so it is connected to baluster. Okay, so B is 4. So as per this, we can say B is the correct option. Okay? So let us see. Even after that, let us see what are the this remaining ones. So what is a finial? Finial is basically, yeah. So finial is basically this top portion. Okay. So at the extreme ends, the big pillars. Okay, in the staircase, the top portion is called the finial. Okay, and the newel is basically that pillar itself, the final at the pillar at the end of the stairs. So that is newel, and above that, at the top of that, the newel cap is basically the finial. Okay, so therefore we can say finial is connected to newel, that is C is 3, so it is going as per B. Okay, and last is the nose and your step. Okay, so that is also correct. Okay, so nose is basically the extended portion, okay, from the bottom of the perpendicular distance from the bottom of the rise, right? So this extended portion, and this is present in where? This is present basically in a step. Okay, so nose is connected to step, so D is 1. Okay, so therefore A is 2. Stringer beam is present in bottom of steps. Handrail is connected to the baluster. B is 4. Okay, so, then yeah, so then final is connected to the top of final is basically the newel. Sorry, the top of newel is basically the final. Okay, so C is basically 3 and nose is basically inside step 1. Okay, so D is 1. A2 before C3, D1 will be the correct choice, that is B. Okay, so B. Okay, B, A2 before C3, D1 is the correct option. Third question, if the sides of a landing slab of a dog-legged staircase are embedded into walls and the slab spans along the direction of the flights, for designing of the slab as per IS 456 2000, one of the following factors that need to be considered is: A, if the slab is embedded into the wall by more than 150 millimeter, a 100 millimeter strip may be deducted from the loaded area. B, if the slab is embedded in the wall by more than 110 millimeter, a 150 strip may be deducted from the loaded area. C, if the slab is embedded in the wall by less than 200 millimeter, a 100 millimeter strip may be deducted from the loaded area. D. If the slab is embedded in the wall by more than 110 millimeter, a 75 millimeter strip may be deducted from the loaded area. So which is the correct option? So the question is, if the sides of a landing slab, okay, of the dog-legged staircase are embedded into walls, okay, so they are monolithically connected with the walls, and the slab spans along the direction of the flights, okay. So then for designing of the slab, okay, so as per IS 456, which factors has to be considered among them, okay. So for finding the answer, we have to go to clause 33.2 of IS 456 2000, okay, that is present in page 63, okay, this clause. So as per this clause, it says that if the slab is embedded in the wall, okay, and by if the embedment is by more than 110 millimeter, then we can strip, okay, we can deduct, basically we can deduct a 150 strip, okay, from the loaded area, because that will be taken by the wall, okay. So that is, if the slab is embedded in the wall by more than 110 millimeter, a 155 strip of the slab, okay, can be deducted from the loaded area, okay. So that will be taken by the wall itself. So that is given in B point, okay. If the slab is embedded in the wall by more than 110 millimeter, a 150 millimeter strip may be deducted from the loaded area, okay. So basically B is the correct option. So as you can see, B, slab embedded in wall by more than 110 a 150 strip may be deducted from the loaded area is the correct option, okay. Fourth question. As per IS 456 2000, in case of an open well staircase, which of the following statements is true? A. Spans with partly crossing at right angles. The load on areas common to any two such spans may be taken as half of the actual load on the spans. B. Spans with partly crossing at right angles. The load on areas common to any two such spans may be taken as two-thirds of the actual load on the spans. C. Spans with partly crossing at right angles. The load on areas common to any two such spans may be taken as one-fourth of the actual load on the spans. D. Spans with partly crossing at right angles. The load on areas common to any two such spans may be taken as one and half of the actual load on the spans. So which is the correct option, okay, in case of an open well staircase? So basically open well staircase is basically any staircase which have like in one story it has basically more than yeah, like at least it has three stairs, okay, more than equal to three stairs, okay. So that results in the if it has say more than three stairs, more or equal to three stairs, so there will be inside, okay, there will be in interior portion there will be a hole basically, okay. So that hole will be open, and that will be basically behaving like a well, okay. So it will be, if we can make some staircase like this, okay, one two three, at least three stairs are there in one story, so this middle portion will be vacant, right? So that is basically an open well, okay. So for this we at least need three stairs, okay. For two it will be dog legged, so there it will not be open well. At least three, if there is three or more than three, there will be open well, okay. So it will be open well staircase for that, okay. So which of the following statements is true? So for finding the answer, we have to go to clause 33.2 IS 456 2000, situated in page 63. So as per that, it says that if the spans, okay, of an open well staircase, if they are partly crossing at right angles at 90-degree, then the load on areas common to any two such spans may be taken as half of the actual load on the spans, because there are two spans, okay, they are connected at right angles and there are two spans. So therefore the load on areas common areas, basically there the loads can be taken as half, because there are two spans, okay, present basically, and they're connected at right angles. So therefore we can take half of the load acting, okay, because the depth has double, okay. So that is as said by the IS 456, okay. A, that is spans with partly crossing at right angles, the load on areas common to any two such spans may be taken as half of the actual load on the spans. That statement as per IS 456 is the correct one, okay? So as you can say, A, spans with partly crossing at right angles, the load on areas common to any two such spans may be taken as half of the actual load on the spans is the correct option. Fifth question. Horizontal and vertical component of a step are known as A. Riser and trade respectively. B. Trade and riser respectively. C. Nose. D. Finial. Okay. So which is the correct option? So we have already discussed many times. The horizontal component is basically called the trade, and the vertical component is basically called the rise or riser. Okay, so therefore the horizontal component trade, vertical component riser. So B trade and riser respectively. Okay, that is the correct option. So B is the correct option. B trade and riser respectively. Sixth question: if T and R are trade and riser respectively of a step, T and R are related by A. T equal to R plus 1, B. T equal to R minus 1, C. T equal to R, or D. T equal to R minus 2. Which is the correct option? Okay. So as I told you, for one this one, for one stair, okay, for one flight basically, sorry, for one flight, the number of trade is one less than the number of rise. Okay, riser. Okay, so that is T equal to R minus 1 for a flight. Okay, so this equation is basically for a flight. Okay, so in that question it was T equal to R minus 2 because there were two flights. Okay, there were two flights in a dog legged staircase. Okay, so but the condition is basically T equal to R minus 1. Okay, so that is the general condition. So as you can see, B is the correct choice. So B, T equal to R minus 1 is the correct choice. Seventh question: a flight of a dog-legged staircase is consisted of total 11 numbers of risers. Height of each riser is 150 millimeter and width of each tread is 250 millimeter. If the edges of the last steps of the flight is supported by a beam spanning parallel to the risers and the both beams have width of 250 millimeter, the effective span of the stair would be how much? A 2750 millimeter, B 3000 millimeter, C 3500 millimeter, or D 2550 millimeter. So we basically need to find the effective span of the spare, okay, of the stair, okay, which basically has which is supported, okay, which is supported basically by a beam spanning parallel to the risers, and the edges of the last steps of the flight is supported by the beam. Okay. So for this case, we need to find the effective span of the stair. Okay. So uh, in this case, basically, this is the rough sketch. Okay, for the question. So here the number of riser is 11. Okay, and this is a basically this is a dog legged, so we are basically considering one flight. Okay, not the two flights. Okay, in the this one, in the story there will be two flights because it is a dog legged, but here we are only considering one flight. So the riser it is 11 and number of trades is one less than the number of rides. Okay, because we are considering only one flight. Okay, so here the total number of trade will be 11 minus 1, that is 10. Okay, and going is how much? It is going will be it will be, yeah, it is 250 mm each trade. Okay, so it will be 11 times sorry 10 times 250. Okay, so the width of the trade is 250 millimeter, and there are 10 threads. 10 times 250 250, so it will be 2500 millimeter. That is the going. Okay, from here to here. Okay, and width of each beam, these are the beams basically. So width of each beam, this and this, they are 250 millimeter. This portion is 250. Okay, so as per clause 33.1a of IS 456 2000. Okay, so as per that clause, for effective span, the effective span of the staircase, okay, which is beams running uh, at the edges, okay, parallelly with the risers. Okay, the axis is parallel to the riser, axis of riser. So in that case, the effective span is basically the span of the stair, which is 2500. Okay, and plus the half of the beam width in both the for both the cases. Okay, so half of this beam width and half of this beam width and the span. Okay, so that is 10 span of stair. So half of the width here is 250 half. Okay, so there's 125, and here also 250 half 125. So 125 plus 125 plus this distance, which is 2500. Okay, so 2500 plus 125 plus 125 for 2500 plus 250, which is nothing but 2750 millimeter. So A 2750 millimeter is the correct choice. Okay, So therefore A, 2750 millimeter is the correct option. Eighth question. A dog-legged staircase is consisted of steps with tread and riser depth as 250 millimeter and 150 millimeter respectively. In addition to that going depth of the steps, waist slab depth and floor finish thickness are 250 millimeter, 150 millimeter and 20 millimeter respectively. If the unit weight of concrete is 25 kilonewton per meter cube and that of floor finishes to 23.5 kilonewton per meter cube, the weight of each step, including waist slab, would be equal to A. 0.470 kilonewton per meter width of step, B. 4.373 kilonewton per meter width of step, C. 1.875 kilonewton per meter width of step, D. 6.718 kilonewton per meter width of step. Okay, so which will be the correct option? So we need to basically find the weight of each step, including waist slab. Okay, so basically and also floor finish is given. Therefore, there will be total of the total weight will be 3, addition of 3. That is the weight of each step excluding the waist slab, the weight of waist slab, and the weight of floor finish. Okay, 3 weights will be there. We have to just add. Okay. So these are the given values. Straight depth of the step T is 250 mm. Riser height of the step R equal to 150 mm. Going depth of the step G is 250 mm. Depth of waist slab, okay, capital D, considered here. So it is 150 millimeter. Thickness of the floor finish TF equal to 20 mm. Unit weight of concrete gamma C is 25 kilonewton per meter cube. Unit weight of floor finish gamma F is 23.5 kilonewton per meter cube. Length of each step along the waist, okay, that is B, that is square root of r square plus t square, right? Rising in your trade. Here trade is basically same as going, okay, because there is no nose. Okay, so there is square root r square plus t square, that is 291.55 millimeter, right? So now we can calculate the three weights. Okay, first is the weight due to floor finish, that is WFF, that as we just discussed, that is equal to TF into T into gamma F by G, right? So substituting the values, we get WFF value as 0.47 kilonewton per meter. The weight of waist slab, okay, that is equal to D into B into gamma C by G. Okay, so substituting the value, we get it to be 4.373 kilonewton per meter. And the weight of each step without the waist slab, basically the equation is half into R into T into gamma C by G. So substituting the values, we get the value to be 1.875 kilonewton per meter. Okay. So therefore, the weight of each step, including the weight of waist slab as well as the floor finish. Okay. So that is the total weight of the each step will be the sum of all the three. Okay. That is sum of 0.470, 4.373 and 1.875. Okay, so adding all the three, we get the weight of each step including waist slab and floor finish to be 6.718 kilonewton per meter. Okay, so that is the answer. Okay, so it is matching with option D. Okay, so we can see D, 6.718 kilonewton per meter width of step will be the right option. Okay, ninth question. A dog-legged staircase is consisted of steps with tread and rise depth as 250 millimeter and 150 millimeter respectively. In addition to that, going depth of the steps and waist slab depth are 250 millimeter and 150 millimeter respectively. So basically, yeah. So basically, if you see here also, going is 250 and tread is also 250. So there is no nose. Okay? So that is completely vertical. The rise is vertical, right? So if the unit weight of concrete is 25 kilonewton per meter cube, the weight of each step including waist slab would be equal to how much? A. 6.248 kilonewton per meter width of step. B. 5.137 kilonewton per meter width of step. C. 7.235 kilonewton per meter width of step. Or D. 2.257 kilonewton per meter width of step, which according to you will be the correct option. Okay, so here also we need to find the weight of each step, okay, including waist length. Okay, but if you see here, there is nothing given about floor finish. Okay, so therefore here the weight of each step will be the summation of two dead loads. Basically, one is the weight of step excluding the waist length, and second is the weight of waist length. Okay, so let us see how to calculate. It will be similar only. So the trade depth of the step T is 250 mm. Rise height of step R is 150 mm. Going depth of the step G is 250 mm. Depth of waist slab capital D is 150 mm. This is not given, they have just assumed. This is unit weight of floor finish also not given, just assume. Actually, we don't need these two values. The unit weight of concrete gamma C is 25 kilonewton per meter cube. Okay. So length of each step along the waist slab B is square root of r square plus t square, that is 291.55 millimeter, right? So as we discussed in last problem also, we just have to calculate the weight of waist slab and weight of each step without waist slab. Okay. So weight of waist slab is the d into b into gamma c by g. Okay. That is substituting the values 0.15 into 0.29155 into 25 by 0.250. So that comes out to be 4.373 kilonewton per meter per meter. Okay. And weight of each step without waist slab. Okay. So calculating weight of each step without waist slab basically. So that is basically w sws. Okay. So that comes out to be the formula basically for calculating, that is half into r into t into gamma c by capital G, right? So yeah, r value is 0.15 and t is 0.25, gamma c is 25, and half into half by 1.25 G. Okay. G value is 0.25. So substituting the values, we get it to be 1.875 kilonewton per meter per meter. Okay. So therefore, the weight of each step, including the weight of waist slab, will be addition of these two, right? So it is 4.373 plus 1.875. That is 6.248 kilonewton per meter per meter. Okay. So if we match the options, we will get that A 6.248 is matching, right? Yeah. So 6.248 kilonewton per meter width of step will be the correct option. So as you can see, A 6.248 kilonewton per meter width of step will be the correct option. Okay. Next, last question. Question number 10. A dog-legged staircase is consisted of steps with tread and riser depth as 250 millimeter and 150 millimeter respectively. Okay. Addition to that, it has total 11 numbers of riser in a flight and a landing slab at one side of its flights. Width of the landing slab is 1200 millimeter and it spans parallel to the risers. What would be the effective span of the stair? Okay, so we basically need to calculate the effective span of the stair. Okay, that is basically as you might remember, that is equal to s plus x plus y. S was the span of the stair, and x and y were the distances that we need to calculate from the landing portion. Okay? So yeah, so what will be the effective span? 3000 mm, 3100 mm, 4000 mm, 4500 mm. Okay. So what will be the correct option? Okay. So as you can see here, the tread depth of the step T is your this one 250 mm. Okay. Riser depth of the step is 150 millimeter. Width of the landing, that is basically the landing slab width is 1200 millimeter. Okay. And total number of riser. Okay. Total number of numbers of riser in a flight is 11. Okay. So yeah, so it is given number of riser in a flight is 11. Okay. And total number of therefore tread in a flight will be 1 minus less like number of riser minus 1, right? So 1 less than the number of riser, so it is 11 minus 1, that is 10. Okay. So as per IS 456 clause 33.1b, okay, page 63. So the effective span, as we discussed, it was s plus x plus y. Okay. So s was basically the number of trade is 10 and the trade is 250 per step. So it will be 10 into 250, that is 2500. So 2500 is the value of s. Okay. And if you see in the question, they have said that landing slab is only at one side of the flights. Okay, a landing slab at one side of the flights. So ideally it should be two sides. Okay, but they have only given one side. That means either of x or y will be 0. Okay, one of x or y will be 0. So let us assume x is 0. Okay, so s plus x plus y becomes s plus y. Okay, s is 2500. Yeah, 2500, 250 into 10, and y will be basically as plus I, as per IS 456, it will be minimum of 1000 and half of 1200. Okay, 1200 is the width of landing. Okay, and that is also like, first we have to check that this value is greater than equal to 1000. If it is not, then directly we take 1000. Okay, and if it is greater than 1000, then we take the half and find the minimum of 1000 and that value. Okay, so because it is greater than equal to 1000, so we have to take this value, we have to take the half of that value, and 1000, and out of that, and find the minimum of 1000 and half of this value. So this value 600, half of this value 600. So minimum of 1600 will be how much? 600 itself. Okay, so therefore y value will be 600. So s is 2500, x is 0, y is 600. So it will be 2500 plus 0 plus 600, or 2500 plus 600, which is 3100 millimeter, right? So if you see here, B 3100 millimeter, it is matching. Okay, so we can say that B is the correct answer. Okay, so as you can see, B 3100 millimeter is the correct option. Okay, so with this we would end today's class. Okay, so I hope that you have understood the basic concepts behind the design of staircase. So next class, I think we will be heading to the design of torsion. Okay, so that is, I think, the last design of limit state design. Okay, how to design for torsion. So based after that, I think like mostly it will be over. Last class, like 12th class, will be mainly on how to use how to integrate all those into a software and how to design a section. Maybe it will be a demonstration of that. So basically, next class we will be dealing with the design of torsion. Okay, so yeah, so with this, I would like to end today's discussion. Okay, so let us meet next Sunday. Okay, so with this, I'm ending today's class. Good night. Yeah.